In this lecture, we're going to look at the theory of vector fields, which are used all over the place in science and engineering. Now, you've already seen in the last topic that a scalar field is a function that assigns every point in space a value. So, for example, a temperature, an air pressure, every single point of space x, y, and z has a value. A vector field does a very similar thing, except it assigns a vector to every single point in space. So you could almost imagine that thinking about, for example, the airflow in the room, at every single point in space I could measure the magnitude and direction of the currents of air at that point. And then I could imagine drawing a little arrow at every single point, pointing in the direction that the air is flowing in. So if the air is flowing quickly, you'd have long arrows. If the air is flowing slowly, you'd have very small arrows. This is kind of a way of visualizing a vector field as a flow. And indeed, we're going to use vector fields to understand flows. Another example of a vector field that we have already seen in this course is the gradient vector. Now remember that the gradient of a scalar field tells us the direction of maximum increase of our scalar field. So if I've got a scalar field phi, it could be the temperature in the room, and then the gradient of the temperature tells me the direction I need to move in to increase the temperature as quickly as possible. And it does that for every single point in space. It also tells me the magnitude of the rate of increase. So the gradient vector also assigns every single point in space a vector. So it's a vector field. So a vector field is simply a vector made up of functions of x, y, and z. Let's take a look at an example of a vector field. So in example 1, we're given a vector field f vector of x, y, and z. And it's a function, a vector, I, j, and k components, where the components themselves are functions of x, y, and z. So if we want to find out what is the value of this vector field, what is the vector itself, at a particular point, all we're going to do is substitute in x, y, and z. This makes it very easy to calculate vector fields. So our vector field is f of x, y, and z is equal to x squared plus y squared I plus x, y, z, j minus e to the x, z, k. So if I want to calculate what is the vector field at the point 0, 2, 3, I'm just going to stick in 0 for x, 2 for y, and 3 for z. Minus e to the 0, z is 3. So we get 4i vector plus 0j vector minus e to the 0, of course, is 1. So we get minus 1 times 3. I get minus 3k vector. And so I can write that in a slightly shorter notation, 4i minus 3k, or I can write that in column notation. So it's very convenient to calculate what the value of a vector field is, what the vector is at a particular point by substituting in the relevant values of x, y, and z. Let's take another look at a different vector field and try and see what that vector field looks like as I look at different points in space. So our vector field, example 2, is a two-dimensional vector field in this case. I don't have a k component, I just have an I and a j component, and it depends on x and y only. So I'm going to sketch what this vector field looks like at different points in space. So let's first of all calculate what those values are, what those vectors are. So let's calculate what the vector field is at the point 0, 0, at the point 1, 1, and so on. And once I've got those vector fields, I'll plot them on a graph. So I have my formula. I've got x plus yi, so that's 0 plus 0I plus 0 squared plus 0 squared plus 1 j vector. And so that will be 0I plus 1j. So that's the value of our vector field at the point 0, 0. And notice again that it gives me a vector. In fact, it's just the vector j. Let's repeat that now for the other points. So I've got 1 plus 1 I vector plus 1 squared plus 1 squared plus 1 is equal to 2I vector plus 3j vector. At the point x is equal to minus 1, y is equal to 1. I end up with, I left off a j vector there. I end up with 0I vector plus 3j vector. For the point x is equal to 1, y is equal to minus 1. I get 0I vector plus 3j vector. And for the point x is equal to minus 1, y is equal to minus 1. I end up with minus 2I vector plus 3j vector. So I have my 5 different vectors here. These are 5 different values of my vector field at 5 different points. Let's sketch what these look like on the xy graph. So I've got 5 points. I've got the point 0, 0. I've got the point 1, 1. I've got the point x is equal to minus 1, y is equal to 1, minus 1, minus 1, and 1, minus 1. So those are my 5 points. Now let's sketch on there what my vectors are. Now when I'm sketching these vectors, I want to make sure that I use the same scaling for each point in space. What I mean by that is, of course, the values of these vectors here aren't corresponding to distances. They're just whatever. They could be, for example, velocities. So I have to indicate here what I mean by I and what I mean by j. Those are not I and j in the x and y plane, they're the velocities. So for example, it could be I is 1 meter per second in the x direction and j is 1 meter per second in the y direction. So let's just show what that looks like. So for example, I could make something this long be I vector and something this long be j vector. And then I'll have to put those together to form my vectors. So at the point 0, 0, I know that t is equal to 1j at that point. So there we get t is equal to j. At the point 1, 1, my vector field is 2I, so 2 units in the x direction, plus 3j, so 3 units in the j direction. So it's going to be something like that. So it's t1, 1 vector is equal to 2I vector plus 3j vector. And I'm just being consistent from each point. So we've got now the point x is equal to minus 1, y is equal to 1. The value of my vector field there was 0, 3, 0i plus 3j, so just 3 units in the y direction. So it's the same height as the last one. So we have that t at minus 1, 1 is equal to 3j. Let's look at the other 2 points. At the point x is equal to 1, y is equal to minus 1, I've got, again, 3 steps in the j direction. And finally, for the point minus 1, minus 1, I've got minus 2 in the x direction and 3 in the j direction. So I'll get something that looks a bit like this. So this is a brief sketch of what our vector field looks like. You can see that at each point that I've calculated a vector field, I've drawn an arrow, and each of these arrows is of the right proportion. They're roughly the same I and j. So you can see that it's quite time consuming to try and draw vector fields or visualize them by hand. And it's best to leave that kind of thing to computers. I'm going to show you in the next figure a plot of the vector field at a lot more points. So this is the same vector field that we were just plotting, and you can see that it has a fairly complicated expression, a fairly complicated form, and in fact, if I try to do three-dimensional flows or vector fields, things get out of hand pretty quickly. So this is an example from example 1. It's a three-dimensional vector field, and it's quite hard to tell what's going on here. I've drawn little arrows at every point, but there's a lot of arrows and they're sort of pointing in every different direction. So we need some tools in order to be able to understand what flows or what vector fields like this are doing. Now we're going to see 3 specific tools for analyzing vector fields and scalar fields. Grad, divergence, and curl. Gradient, divergence, and curl, or for short, grad, div, and curl. Gradient, of course, you've already seen. It's a way of calculating the rate of change of a scalar field with space. So let's just remind ourselves of how grad works, and we're going to introduce it in a slightly different way from the way we saw it in the last topic. In the last topic, we introduced gradient as being the vector made up of partial derivatives of phi. Here, however, I'm going to write it slightly differently. I've introduced again this upside down triangle symbol. I call that nabla or del. So we call this nabla or del, and it can be written as what looks like a vector. It's got I, j, and k components, except instead of having numbers or even functions as its components in x, y, and z, it's got partial derivatives. Partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. So clearly this vector, del or nabla, doesn't have a meaning on its own. What it gives us is a meaning when I apply it to other vector or scalar fields. So in the case of the gradient, I've written the gradient as almost like the product of a vector and a scalar. So basically I've applied multiplied a component phi by each of the components ddx, ddy, ddz. Now of course this isn't actually multiplication here, because what I'm actually doing is taking derivatives. I'm applying a derivative to phi. So I can sort of build up gradient just from this del operator, this differential operator. Now you can see that it's completely equivalent to the vector of partial derivatives, but the advantage is going to come in when I introduce these other vector operators, divergence and curl, which are going to be expressed in a very simple form using del. Let's remind ourselves again of the gradient. So let's calculate for this case what the gradient of this scalar field is. So I've got the gradient of phi. Phi was equal to x squared y squared z plus 2y. So the gradient will be the derivative with respect to x plus the derivative with respect to y plus the derivative with respect to z. So that gives me a vector field. So notice there that I started with a scalar field and I ended with a vector field. And that's one of the characteristics of gradient. Gradient takes a scalar field and gives us a vector field. We can use that as a check to make sure that we've correctly calculated the gradient. Now let's look at our next operator, divergence. So divergence is something that takes a vector field and gives us a scalar field. So I'm going to be given a vector field f of x, y, and z. It's the same vector field we saw in example 1. And I'm going to write that as I, j, and k components. So f1, f2, and f3 here are functions of x, y, and z. So I'm going to form a scalar field by adding together the partial derivatives of f1, f2, and f3. That is, partial derivative of f1 with respect to x plus partial derivative of f2 with respect to y plus partial derivative of f3 with respect to z. So notice that immediately that we're going to get a scalar field from this because these are all scalar functions. And notice also that if I use the del operator here, I can make the divergence or div of f look kind of like it's a dot product, right? It looks kind of like I've got d dx multiplied by f1 plus d dy multiplied by f2 plus d dz multiplied by f3. Of course, again, I'm not multiplying here. I'm applying a differential operator. But it does kind of look like if I write it out, a dot product. So the del operator is d dx I vector plus d dy j vector plus d dz k vector dotted with f. So f was f1 I vector plus f2 j vector plus f3 k vector. So carrying out that dot product, I get first component plus second component plus third component. And notice that just like the dot product takes two vectors and gives me a scalar, the divergence, which I can think of as kind of like the dot product of del and f, takes a vector operator and a vector field and gives me a scalar field. Now in the next lecture, we'll talk about what the divergence operator actually tells us. What's the physical significance of the divergence operator? You can probably tell from the name, it's got something to do with flows that are diverging or converging at a point. And we'll show that explicitly in the next lecture. For the time being, let's just try and understand how we can calculate this divergence. So I've got my scalar field, my vector field here, and I'm going to calculate the divergence by calculating the derivative of the first component with respect to x, second component with respect to y, and third component with respect to z. So f1 is equal to x squared plus y squared, which means that the partial derivative of f1 with respect to x is equal to 2x. f2 is equal to xyz, which implies that the partial derivative of f2 with respect to y is equal to xz. Last one, f3 is equal to minus e to the x times z, k vector, which implies that df3 dz is equal to minus e to the x. So I can put these things together to form the divergence. And that's going to be equals to 2x plus xz minus e to the x. So that's my divergence. And again, notice that I ended up with a scalar field, something that assigns a scalar value to every point in space. The last operator that we're going to look at is curl. So the curl operator is going to take another scalar vector field, f, and it's going to calculate a determinant, just like the cross product. So again, notice that I've written the curl as what looks like the cross product of the del operator and my vector field. And again, what I've done is I've written, for calculating a cross product, I, j, k. I've got the components of del in the middle row and the components of f in the bottom row. So it looks a lot like a cross product, and I'm going to calculate this in exactly the way I calculate a cross product. So let's take a look at that. So the curl of a vector field f is equal to the cross product of del with my vector field f. So writing that as the determinant of a 3 by 3 matrix, I've got I, I've got j, I've got k across the top, I've got partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z in the middle row. So those, of course, are the components of my operator del. And I've got my components of f. So we've got 3y, I've got xz, and minus x cubed in the bottom row. Those are the components of my vector field f. So let's calculate that cross product. So the first component will be I vector. So it'll be, let's just go through it explicitly here. So I've got this multiplied by the determinant of this 2 by 2 matrix. So that's going to be I vector times the partial derivative with respect to y of minus x cubed. So we've got those diagonal terms first. And notice that I have to be careful with the order, because the partial derivative, of course, is applied to the function of x, y, and z. So we've got the partial derivative with respect to y of minus x cubed. Minus, now let's do the opposite direction, partial derivative with respect to z of xz. Partial derivative with respect to z of xz. And again, notice that I'm being careful here with the order because, of course, the partial derivative is being applied to the function of x, y, and z. So I need to have the partial derivative first. Next term, we can write this as minus j times the determinant of this 2 by 2 matrix made up of these columns. And again, I'm going to be careful here when I order this so that I have partial derivatives being applied to functions. So I've got minus j vector. The first component is going to be d dx of minus x cubed. Partial derivative with respect to x of minus x cubed. Minus the partial derivative with respect to z of 3y. Partial derivative with respect to z of 3y. Plus k vector. Let's do the third one. So again, we've got k vector multiplying the determinant of this 2 by 2. So I've got k vector of d dx xz minus d dy of 3y. So I have a bunch of derivatives there to do. Let's write those out. So I get I vector. Partial derivative with respect to y of minus x cubed will be 0, because that partial derivative treats x cubed like a constant, minus the partial derivative with respect to z of xz, so that will be minus x, minus j vector, partial derivative with respect to x of minus x cubed, so that'll be minus 3x squared, minus d dz of 3y, which is 0, plus k vector. I've got the derivative with respect to x of xz, minus the derivative with respect to y of 3y. So that's going to give me minus x I vector plus 3x squared j vector plus z minus 3 k vector. So you see that what I ended up with here was another vector field, right? I've got I, j, k, and those components are functions of x, y, and z. So this is going to give me another vector field. So just like the cross product takes two vectors and gives me back a vector, the curl is going to take a vector operator, del, and a vector field, f, and give me a new vector. And as you might guess, the curl has something to do with rotation in a flow, as we'll show in the next lecture.